George, it's a great honor. You're a giant of science. It's such an honor to be here. Congratulations on being at the Collège de France for a year. And we've only seen the first part of your career, correct? You have so many more contributions to make, and you're just brilliant, and it's been such a pleasure to know you over the decades. So thank you very much for having us. Thanks to Raul. By the way, you have very handsome children. I wish mine were half that handsome. So what do you feed them? And Johan, it's been a pleasure to listen to what you're talking about. And both of you gave these wonderful overview talks. And you both mentioned environmental degradation, and that's what I'm going to concentrate in this, my presentation. Except I'm going to do it from a much more fundamental point of view. Hope you don't mind. Although I'll keep it still at a very high level and just sort of gloss over extremely detailed and complex chemical issues that have to do with nanoscience. So about 25 years ago, I started looking at, my wife's from Montana, there's a lot of mining in Montana. I started to look at some of the largest contaminated areas in the world that are in Montana due to mining, horribly contaminated lands, vast reaches of wonderful, beautiful land that was affecting the health of tens of thousands to hundreds of thousands of people, let alone fish, bear, wolves, coyotes, all the way to microorganisms. And I would ask the geochemists working on these, because I'm a geochemist, how does the pollutants from these mines get so far away from the mine site, sometimes hundreds to even thousands of kilometers away, when geochemically it makes no sense at all? And so my first several years, 25 years ago, of looking at these systems were failures. I couldn't figure out where the contaminants were, exactly how they were tied up in the sediments that surrounded the mine sites, the rivers that flowed from the mine sites, the atmosphere around above the mine sites. I couldn't even find how the contaminants were tied up in water, in sediment, in soil. And when I asked geochemists, they didn't know either. And so about that time, I became involved in nanoscience, which is an emerging science, as you know. And let me go to this next slide, which gives you an idea of what we do in our group. And you see nanoscience and technology right here. But this is where I started, in earth and environmental science. And I tried to become a molecular biologist, because these days we're working on surface science of the earth. You need to understand this, and you need to have molecular biology labs, because if you don't, you're missing a huge part of what's going on. So we've done that. We do everything from synchrotron work, although Gordon will talk about this next. They were the ones that invented these methods for earth science. We do aerial reconnaissance. We especially do a lot of transmission electron microscopy, not just for the microscopy part, but for the spectroscopy part and the diffraction part. And using all these together, and if you have $6 or $7 million of your own money to spend, because governments supply these, you have to buy these, and they're really expensive, really difficult to use. But over the years, we've been successful at that. And so with this, you can do some of the best nanoscience that's ever been done. We do a lot of field work, and so on and so forth. So I'm going to talk about mine contamination, why contaminants move and work the way they do around mines, which hopefully in the future will help us remediate this contamination much more intelligently than we presently do. Okay. We've seen this a lot yesterday, right? This was almost in every talk. What nanoscience does is it takes this, which we think we know really well, and it completely transforms how we understand the periodic table. And what nanoscience does is it does this. It takes the periodic table and it makes multiple periodic tables. In fact, this is a great oversimplification. It's even much more complicated than this. This is why nanoscience is an industry that today is worth $1 trillion per year. And in 5 years, it will be up to the $3 trillion level. You need evidence for this. All you have to do is reach in your pocket and pull this out. This has 8 million nano devices inside of it. they're called field effect transistors. And they're nano-sized transistors, and they work on principles of electronic conduction and nanomaterials. All we're doing is taking this nanoscience and applying it to earth science, and we apply it to every kind of earth science you can think of. In this case, obviously, we're going to talk about mining. Now, it used to be in mines, you would go to the field and you would take water samples in a river, and you'd go, oh, the arsenic concentration is high in this river, or the lead concentration is high in this river, or in the sediment. And you would take that water and you would filter it with a 0.22 micron filter or a 0.45 micron filter, very commonly done for decades by geochemists, field geochemists. And I'd say, well, you just filtered water that went through 220 nanometer holes in your filter. And they're saying, yeah, and all the metals in that water are dissolved. And we immediately said, that can't be right. This is a dissolved metal right here. There's a metal atom surrounded by so many oxygens or so many water molecules, and then everything out here is H2O. That's only 7 atoms there. What if you put 3 of these together to make 18 atoms? Does this behave like this? And as someone who has worked with quantum mechanics as well, and a lot of physical chemistry, this is not this. They behave very differently. How about if you take one of these, in this case this is an octahedra, which you can make into a solid form. So this piece right here is now represented by that polyhedron right there. And so now we have, what is it, like 12 of them? And if that's only 1 layer thick, you have about 150 atoms. So you're getting a number of atoms really fast now. That's only 1 nanometer in size. That's a 1/100th of a micron. Or you can make it this big. This is 5 nanometers in size, and now we've gone up to about 1,000 atoms. But all of these would have easily made it through that filter, and this is what geochemists used to call pure dissolved metal. But in fact, it's this, or this, or this, or this, or bigger, or bigger, or bigger, before you get 220 nanometers in size, which is way bigger than that. And they were all calling that the same thing, and clearly that's not right. So we have to rewrite geochemistry now to understand the behavior of this, the behavior of this, and this, and this, and all these other forms until you get to macro size. Well, in nanoscience, this is what nanoscientists study. And so the properties of all these things are very different as a function of size and shape. And that's all nanoscience is, whether it's in my iPhone or whether it's contaminants in the field. So if this is a contaminant element, metal right here, then you're really interested in the behavior of all of these things and how they move through the environment. And if that's the only thing you take from my talk, that would be worth it. This is earth science of the future. We have just started it. In all fields of nanoscience, electronics, magnetics, the physical properties of nanomaterials that we use, the research has just started. It's going to go on for literally decades to centuries more, and that couple of $1 trillion will be nothing in the future in terms of the value of nanotechnology to society. Okay. Nanocrystals we define as between 1 nanometer in size and 100 nanometer in size. But over the last decade, we found out that it's really the smallest nanocrystals that we're most interested in because these have the most unusual properties. So you can take a mineral that you know and love and you think you know all the properties of that mineral. Say hematite, iron oxide, very simple. But when you make that same hematite macrocrystal into a 5 nanometer crystal or a 10 nanometer crystal, which by the way exists in nature all over the place as we're finding, they have completely different properties just because of the nature of their small size. Again, that's the fundamental aspect of nanoscience. So here are nanocrystals. This is periodicity in terms of short range order, medium range order, long range order. I've already taken way too much time and I'm not going to get into this. But the point being that with these small crystals that we're finding now ubiquitous in nature, and especially in this case in mining contaminated areas, you get all kinds of not these perfect things that I was showing you in the last slide. Some of these are nanoclusters. Some of them are amorphous in nature. They might be a couple of nanometers big, by the way, 10 angstroms is 1 nanometer. Their atomic ordering is very disordered, and we call them amorphous. Sometimes we get materials like this. You can't see it very well, but we call it polyphasic nanomaterials. This is a new invention or discovery that we've made, where a lot of materials are made of nano clusters of highly ordered material surrounded by nano areas of much less ordered material. Or it can be like this, where you have wonderful ordering in a very small nanoparticle. In this case, it's only a couple of nanometers big. But the surface is highly disordered and probably has a slightly different chemistry than the inside of that nanocrystal. And this is the only really fundamental science I'm going to show you. But let me just say that if you take one of these and you look at the energy of the electrons in the valence and conduction bands, this is energy increasing from here to here. And here are the valence band electrons. As you know, these are bonding electrons, anti-bonding electrons, non-bonding electrons. This is what controls the property of materials. And then you have this band gap if it's a semiconductor, like this TiO2 is. And then you have the conduction band electrons. And again, this is how the field effect transistors in your phone work, by electrons jumping from the valence band to the conduction band and back. Well, when you take a perfect material, it might look like this. But when you take a defective nanomaterial, these bands are not so beautiful anymore. They look like this. And that's what's changing the physical and chemical properties of these materials dramatically. Just by these few electrons at these particular energies becoming this mush right here. Now the band gap is no longer 3.3 electron volts, it's now 1.5 electron volts, and this poor semiconductor has become an excellent semiconductor and very photocatalytically reactive. And you don't want that in nature, because this does nasty things to organisms, including humans. And this is just photoelectron spectra that shows that we're not just playing with models here. You can calculate this. But the spectroscopy actually even shows that the black one is this here, the red one is this part right here. And so you can actually see these spectroscopically, and that's why Nobel Prizes have been given for the developers of, say, photoelectron spectroscopy. Okay, and there are some other things going on. This might be more easily understandable. These, and speaking of hematite, iron oxide, these are iron oxide nanomaterials taken by what we call HOTF STEM, very new generation of technique that you can use in electron microscopes if you have the very best microscopes. They cost a whole lot of money and require a whole lot of experts to run. And so these are three-dimensional images of these hematite crystals, iron oxide crystals, which are only about 20 nanometers in size. Each of these is about 20 nanometers in size. And you see these green channels in there. And these are nanotubes or nanopipes within the crystal. So you're looking at almost a holographic view, a tomographic view, like an MRI taken in your body, using math that was discovered a long time ago, now applied in a very modern way. And look at what these tubes are like. If I can wake my computer up and let these crystals spin, and you can see the nanotubes inside, which are only about 2 or 3 nanometers in size. And just the fact that these nanotubes are there makes these hematite nanocrystals behave completely differently than nanocrystals of hematite that don't have the nanotubes. The nanotubes are highly chemically reactive. And again, these are void spaces, tubes that go into the crystal, and they're only 2 nanometers wide. And we can see them easily in this kind of electron tomography. Another fundamental principle of nano that we've been working a lot on over the last decade is how many naturally occurring nanomaterials are on the planet. How many nanomaterials are made naturally, and where do they go? So here are the continents and continental shelves, oceans. Here's the atmospheric. And all of these numbers are teragrams of nanomaterial. So let me tell you, for example, I could talk for a week on this one slide. In fact, this one slide it describes a 50-page chapter in a book that we wrote. From the continents to, say, the oceans just offshore. Every year, rivers bring 1,000 to 10,000 teragrams of nanomaterials that are made in soils naturally to the oceans. And 1 teragram is 1 million metric tons. So that means that every year there's 1,000 to 10,000 million metric tons of naturally occurring nanomaterials that are made naturally in soils, and they're brought to the oceans, and they do a lot of chemistry in the oceans. For example, these things come off, these are iron oxides that come off continents into the oceans. They provide a limiting nutrient to phytoplankton in the oceans, that is iron, which is highly insoluble in seawater as an ion, but these nanoparticles are all over the place, and these microorganisms just figured out ways to get that iron into their system so they can photosynthesize. And that changes the temperature of the whole planet, because these are photosynthetic, that are photosynthesizing more than all the land plants combined. They're drawing down CO2 in the ocean, which draws it down into the atmosphere. So this is a planet cooling method. And if these things don't make it to the oceans aren't as planet cooling because these things aren't as abundant. And then you think we have climate change now? It would be much more severe if this cycle was ever retarded. All right, so one more thing. The world of nanomaterials, there are natural ones, I've just talked about those. There are also anthropogenic ones that we make. And this is getting now to the mining part. In the anthropogenic nanomaterials that we make, there are ones that, like, say, go on an iPhone. They're made on purpose, obviously. They're manufactured nanomaterials. But there's also 2 classes of anthropogenic nanomaterials that are called incidental nanomaterials. These are nanomaterials that are made by people, by industry, but by accident. We don't intend to make them, but by the fact that we have industry doing something, like mining, we are going to make nanoparticles that would not otherwise be there. And these ultra-hyper-reactive particles have now entered the environment, and they can do good things, and they can do really bad things. So that's the point of the mining contamination that I'm getting to. So these are incidental, by accident, nanomaterials, and there are 2 types. There's direct nanomaterials, like, for example, you start your diesel automobile, and smoke comes out the back. And there are nanoparticles in there that were just made in the exhaust process. You did not intend for them to be there, but there they are in the air, and you're breathing them, and you hope that they're not going to hurt you. That's called a direct incidental. And an indirect incidental, and by the way, these are our definitions. Hopefully these will stand the test of time, and you'll read about them in textbooks in the future. These indirect incidentals are what mines can make. And these are nanoparticles that form as a result of anthropogenic earth modification, like building a mine, followed by natural production of nanomaterials that would not have occurred without that original human impact. So there you go, you put the mine in, you put the processing facilities in, and all of a sudden in a couple of years, whatever you did to the landscape and the chemistry of the landscape, nature is taking that back over, and it's producing nanomaterials that we never even knew were there. And there they are, and some of them are highly degrading to the environment. And that's where the degradation of what we've found, where most of the degradation of mine waste, that's how it starts, through this indirect incidental formation. So, to finish my talk, and I'm at 16 minutes, John, so that means I have like 10 minutes left or so, is that right? Sure. Should I make it? I can make it faster if you'd like. What time is it? More discussion, better. Okay, yeah, let me see what time it is, because mine talk was going to be, yeah, okay. Okay, I see. I'm going to go through this very quickly, because I'm only 8 minutes from coffee break, and so let me finish this very quickly. 3 really quick examples. The Iberian Pyrite Belt, that is the southwest corner of Spain, which is here, rivers coming to the sea. These have been mined since Roman times, and we look at systems like this, and sure enough, nanoparticles all over the place that have never been described. But why are they important? Here's what some of them look like. This is the mineral Schwartmanite. Wait till you see what this looks like in a tomographic image. It looks like some strange organism from Mars, and these needles that you're seeing here are only a couple nanometers in diameter, and they take up arsenic. And they transport vast quantities of arsenic, more than any other river in the world, to the ocean on the surface of these needles. We never knew that before. We never knew where the arsenic was or exactly how it moved. This is how it moves. Second example, a mine in former Eastern Germany. Now, after reunification, this mine it was a East German Soviet uranium mine where they pulled over 100,000 tons of uranium. Had at one time an employment force. Look at the size of these tailings piles. I think they set a world record. 150,000 workers during the Cold War pulled uranium out of the ground and made an unbelievable mess, which the unified Germany, after 1990, spent $8 billion to remediate. But the remediation is never perfect, and they still have metal contamination going away from this site. And all we did was discover how that happens. These are nanocrystals of green rust. This is ferric ferrous oxyhydroxide sulfate mineral. It's nanometer in this, but these sheets are only 1 nanometer thick. And we found that these are the carriers of the zinc and nickel that come out of the leaking part of the remediation that didn't work and is still contaminating rivers in Germany. So there's a lot I could talk about here, but I'm going to skip all this. This is really interesting material. Only the second time that these materials have ever been found in groundwater in nature, and we were able to do this. Carol Johnson did this for her PhD dissertation. And the last example, the Clark Fork Superfund Site in the United States. This is between Butte, Montana, Anaconda, Montana, and Missoula, Montana, this river, Clark Fork River right here. This is the largest Superfund site in the United States, the largest mining contamination site in the United States. 1,700 square kilometers of horribly contaminated land. They've spent now over $100 million to remediate it, because otherwise this is pristine mountains and fishing streams that people come from all over the world to recreate in. And just an exploded map of this Superfund site. And again, the spread of contamination in this area. This is just out of the river, of the Clark Fork River. These are nanoparticles of goethite that are carrying arsenic and zinc. And if you drink this water, and you'd never know it, I mean, the water looks perfectly clear, tastes fine, but if your body can remove this arsenic and zinc from these nanocrystals, then it will be toxic to you, or an organism, a microorganism, or a fish. If these are not bioavailable, then they just pass right through, and they won't hurt you. So this kind of thing is being studied in our group right now. And again, very interesting story here, but I'm going to skip it and go right to the conclusion. Just a cartoon, but now we can look at these cartoons that we didn't even make. That's Martin Hasselhoff and Frank Vanderkamer in Vienna and Sweden, who draw these cartoons, these wonderful cartoons. Now we know so many more details than this cartoon would present. And the grand challenges then, the last two slides are very simple. Grand challenges are understanding the smallest, less or least abundant, less or least crystalline phases that are driving these dramatic reactions that we're seeing. Sometimes we see nanocomponents that are 0.1% of the sediment, but they are driving 99% of the dangerous chemistry in that sediment. Did you get that? 0.1% concentration driving 99% of the dangerous chemistry in that sediment or in that river water. Or in the atmosphere, same thing. They're hyperreactive materials. Identify and study the phases that are capable of this hyperreactivity. We've just started to do that. There's so much more to do. And the last thing is to understand more thoroughly the biological interactions of nanomaterials. And I could give a whole course just in this one slide where you have nanomaterials. These are iron oxide nanoparticles that are on the surface of single bacterial cells. And in this case, this bacteria is respirating not on oxygen, but on reducing iron that is in the ferric iron oxides on the surface. And we can look these are zinc sulfides that are produced by bacteria, nanocrystals, obviously, And see these defects. See these lattice fringes should just be going straight through, like over here. Just they're straight, should be straight lines. But they zig and they zag in here. These are called dislocation faults. And these defects and many other kinds of defects are what provide the hyperreactivity of these zinc sulfides and release huge amounts of zinc to solution that you would then drink and in time would make you quite ill. Okay, so that's it. Thank you again, and I'll be glad to answer any questions.